Welcome to G Fun Facts Online. Look at the screen you're probably using to listen to this. Your phone, your monitor, your TV. It's brilliant, sharp, and millions of times better than the screens of just a few decades ago. But what if I told you we're about to hit a wall? We're reaching the physical limits of how small we can make the pixels that create these images. But a new revolution is happening, not by shrinking the old technology, but by reinventing it at a scale almost too small to imagine. We're entering the world of Nano-Light, where scientists are building the world's smallest pixels, pixels so tiny they could lead to displays indistinguishable from reality itself. This isn't just about sharper phone screens. This is about displays that could be flexible enough to wrap around a coffee mug, transparent enough to be built into your windows, or even small enough to be woven into your clothes. Today, we're diving into the three revolutionary paths that are making this science fiction a reality: plasmonics, quantum dots, and metamaterials. So our journey begins with a fundamental problem. For decades, progress has meant one thing: packing more pixels into the same space. But as we shrink them down to the micrometer scale, things get messy. Pixels start interfering with each other in a process called crosstalk, blurring the image. The manufacturing becomes incredibly complex and expensive. We're trying to build a skyscraper with grains of sand, and the physics is starting to fight back. This is where Nano-Light offers a completely new playbook. Instead of just making things smaller, scientists are using the weird and wonderful rules of quantum mechanics that take over at the nanoscale to control light in ways we never could before. Let's explore the first of these new methods: plasmonics. Plasmonics is not about creating new light. It's about mastering the art of manipulating the light that's already around us. It's about creating what's called structural color. The color isn't from a pigment or a dye, but from the physical shape of an object at the nanoscale. And believe it or not, this technology has ancient roots. Take the Lycurgus cup, a 4th century Roman chalice. In normal light, it looks a murky green, but shine a light through it, and it glows a vibrant ruby red. The Romans didn't know why, but they had accidentally mixed gold and silver nanoparticles into the glass. They had stumbled upon plasmonics. The magic behind this is a phenomenon called surface plasmon resonance. Here's a simple way to think about it. Imagine a metal nanoparticle. When light hits it, the light's energy can make the electrons on the metal surface vibrate together, like ringing a bell. This collective ringing is a surface plasmon. And just like a bell has a specific note it likes to ring at, these nanoparticles have a specific color of light they resonate with very strongly. At that resonant color, light is heavily absorbed and scattered. By changing the size and shape of the nanoparticle, you can change its resonant frequency. You can tune the color it reflects. Smaller particles tend to scatter blue or green light, while larger ones scatter red or orange. So to build a plasmonic pixel, you create a precise grid of these metallic nanostructures, things like nanorods or nanodiscs made of gold, silver, or even aluminum. The size of the rods determines the color. This allows for mind-boggling resolution, with pixels just a few hundred nanometers across, far smaller than anything possible today. But a static image, no matter how high-res, isn't a display. The real challenge is making these colors change on demand. Researchers are working on some ingenious solutions. One idea is to embed the nanostructures in a flexible material. Stretch it, and you change the spacing between the structures, which in turn changes the color. Another approach integrates liquid crystals, the same stuff in your LCD TV, around the nano antennas. Applying a voltage changes how the liquid crystals bend light, altering the plasmon resonance and switching the pixel's color. One of the most promising methods uses an electrochemical reaction. Researchers at the University of Cambridge created pixels by coating gold nanoparticles in a special polymer. A tiny jolt of electricity changes the polymer, which changes the color. The best part? It's bistable, meaning it holds its color with no power at all, only needing a sip of energy to change. This points to a future of ultra-high-resolution reflective displays that are incredibly energy efficient because they just use the ambient light in the room, no power-hungry backlight needed. Now, if plasmonics is about manipulating light, our second technology, quantum dots, is all about creating it with perfect precision. These are the tiny crystals behind the QLED in your next TV. They are minuscule semiconductor nanocrystals, often just a few nanometers wide. Their ability to glow with pure, vibrant color is a direct result of a quantum mechanical effect called quantum confinement. In a normal, bulk piece of semiconductor, electrons have a lot of room to move around. But when you shrink that material down to the size of just a few atoms, the electrons get trapped, or confined. This radically changes their energy levels. Instead of a smooth range of energies, they are forced into discrete, specific levels, like the rungs on a ladder. The smaller the dot, the further apart the rungs on that energy ladder are. When you energize a quantum dot, say with light, an electron jumps up to a higher rung. When it falls back down, it releases that energy as a single photon of light. The color of that photon depends entirely on the distance it fell, the gap between the energy rungs. And since the size of the dot determines the spacing of the rungs, you can precisely tune the color of light it emits, simply by controlling its size. It's astonishingly elegant. Smaller dots have a big energy gap and emit high-energy blue light. Make the dot a little bigger, the energy gap shrinks, and it emits green light. Bigger still, and you get red. In today's QLED displays, quantum dots work through photoluminescence. A backlight of blue LEDs shines light onto a film containing a mix of red and green quantum dots. The green dots absorb some blue light and re-emit it as pure green. The red dots absorb some blue light and re-emit it as pure red. The remaining blue light passes straight through. Mix that pure red, green, and blue, and you get a brilliant, high-purity white light source that produces a much wider range of colors than a standard LED backlight. But this is just the beginning. The ultimate goal is a true QLED display, an electroluminescent one. In this design, there's no backlight at all. Each tiny quantum dot is its own individual pixel, lighting up when hit with an electric current. This would lead to displays that are even more efficient, thinner, and more flexible. Researchers are making huge strides, creating more stable and efficient quantum dots, even getting rid of toxic materials like cadmium that were used in early versions. The future is nanopixel QD displays, where every single light-emitting dot is patterned at the nanoscale, redefining visual fidelity all over again. Finally, we arrive at our third and most exotic path, metamaterials. If plasmonics and quantum dots are pushing the boundaries of physics, metamaterials are rewriting the rulebook entirely. These are not materials you dig out of the ground. They are artificially engineered structures, designed to have properties that don't exist in nature. The concept goes back to 1967, when physicist Victor Veselago theorized about a material that could bend light in the wrong direction. For decades, it was pure theory, but in the early 2000s, scientists finally built one. They do this by creating a precise, repeating pattern of tiny structures or meta-atoms that are much smaller than the wavelength of light. Things like tiny split-ring resonators or metallic wires. The collective response of these millions of meta-atoms to a light wave gives the material its bizarre, engineered properties. The most famous property is a negative refractive index. This allows for things like a superlens that could see details smaller than the wavelength of light, shattering a fundamental limit of optics. It's also the principle behind the headline-grabbing idea of an invisibility cloak, which would work by bending light waves perfectly around an object. So how do you make a pixel out of this? You use a 2D version of a metamaterial, called a metasurface. By patterning a flat surface with an array of these nanoantennas, you can control the phase, amplitude, and polarization of light with incredible precision. This technology could enable true 3D holographic displays with a wide field of view, just like you've seen in the movies. Their compact, flat nature also makes them perfect for augmented and virtual reality headsets, replacing bulky lenses with something wafer-thin. Of course, this is the most futuristic of the three paths. Designing and fabricating these intricate sub-wavelength structures is incredibly complex and expensive. But as manufacturing techniques improve, metamaterials could offer a level of control over light that we're only just beginning to comprehend. So we have three incredible technologies on the horizon. Plasmonics offers ultra-high-resolution, power-sipping, reflective displays. Quantum dots promise perfect, vibrant color in super-efficient, emissive screens. And metamaterials open the door to a future of total light manipulation, from holograms to invisibility. The road ahead is not easy. The biggest hurdle is manufacturing. How do we cost-effectively build trillions of these precise nanostructures? We also need to ensure these new materials are durable and stable over many years. And we have to figure out how to wire and control billions of individual nanopixels. But the potential is immense. We're on the verge of a world with true 3D holographic communication, smart windows that can turn into screens, and wearable displays woven into the fabric of our lives. The quest for the smallest pixel is pushing us to master the fundamental nature of light and matter. The future of displays won't be measured in inches, but in the infinitesimally small, vibrant, and shimmering world of nanometers. Thank you for listening to Fun Facts Online.